In the last session, we learned how to take the Laplace transform of any given function using this integral. When you are given a function, the only condition about the f was the continuity. I can use this integral, this improper integral, to find out the Laplace transformation. And then I apply to the sum of the functions, if you remember, right? And then I found this. These are the two functions I showed to you, right? The Laplace transformation. Of course, we can ask, okay, some other question. What is the Laplace of this one? What you need to do, you need to put this function into this integral, and then you need to solve it. If we can do it, it's going to be equal b over s squared plus b squared, when s bigger than 0. So I can do the same thing for this function, and then this time the Laplace of cosine bt is going to be equal s over s squared plus b squared. And the last elementary function I can share with you, t to the n. The Laplace of t to the n will be equal n squared over s to the n plus 1. So I found all of the Laplace transformation using that integral. But as you know, it is so difficult to figure out what that integral is. And then also it is so expensive, right, to find out the Laplace using this technique. But for the elementary function, I need to do that. Later, we're going to give up using this technique, and then we're going to collect all these Laplace transformation of these elementary functions in a table. Let me share this table with you. This table is called the Laplace table, and then I shared this table in my email, and then you are going to be free to use this table in any exam, including the final exam, guys. As you see, right, this table includes all the functions, right? Look at that. For example, the Laplace of 1 is equal 1 over s. You need to read in this way, guys. So you can read the Laplace table from left to the right. So Laplace of 1, Laplace of 1 is equal 1 over s. Laplace of e to the at is equal this one. Laplace of sine bt is equal this one, as I gave in my notes. So from now on, instead of using the integral, we're going to start using these type of table so that you can read easily. Of course, if I ask you, please use the definition to figure out what the Laplace of this function is, you just need to use the integral instead of the table. These are the definition, result. So we use the definition of the Laplace transformation, and then definition includes the improper integral. That's good, right? We just put everything into a table. Now we're gonna use the table, and then we created a table for some functions. But what if I ask you this question? Laplace of 3 plus e to the 3t minus 2 cosine 2t. What would you do? Yes, I know, the individual function Laplace transformation, but when I add them, still I don't know, how to solve it. I can use the integral feature, yes, to create a rule for this one, and Laplace will will satisfy that rule, and then we're going to call that rule, guys, linearity of Laplace transformation. What do we mean by linearity? Let me give it to you by definition, and then you can prove it easily. I'm going to skip that part. Let f1 and then f2 functions, and then I know their Laplace transformation exists. And then I have a constant around. Then for s bigger than alpha, Laplace transformation will satisfy these two nice rules, guys. Look at that. The Laplace of the sum of two functions is equal to sum of the Laplace of these functions separately. So Laplace of f1 plus Laplace of f2. And then second feature is about the constant multiple. Instead of multiplying the constant inside, you can take this out and then you can multiply the constant later. This is what we call the linearity of Laplace transformation. And when you have such a transformation, as I showed you in the previous example, I'm going to use these linearity. So what was the example? Example was this one, 3 plus e to the 3t minus 2 times cosine 4t. Let's apply the Laplace linearity. So linearity, because of linearity, right? I can write this Laplace in this way. And then minus, look at that. Also, I can use the linearity feature, the second linearity feature, for this constant. I can take this out, and the rest is just going to be the Laplace of the function I have. The Laplace of cosine 4t. Can I do the same thing for the first function? Why not? 3 Laplace of 1, since I just now derived the Laplace of 1 instead of Laplace of 3. So let me take the Laplace of all these functions. So what is the Laplace of e to the 3t? From the table, you can see it. 1 over s minus 3 minus 2. And then the Laplace of cosine 4t is equal s over s squared plus 16. And the only function I didn't take the Laplace was the first function, 3 times 1 over s, and I have the rest. This is the Laplace of this, right, linear function. And I just used, I used the linearity, right, to take the Laplace of this function, which was given, right, using the arithmetic operations. We can solve one more. Another example. Laplace of 3t squared minus 5 sine 4t minus 7 e to the 2t. Okay. The first part of the linearity can be used, right, to separate these functions, 3t squared. And also I can take the constant out in this way, negative 5 Laplace of sine 4t, and then minus 7 Laplace of e to the 2t. I can also take this out as well, right? Now, I'm going to go to the table and then I'm going to read what is the Laplace of t squared. If you look at that, the Laplace of t squared is equal to factorial s cubed. And then minus the Laplace of sine 4t, here b is equal 4 over s squared plus 16, and then minus 7 1 over s minus 2. We're going to need a lot of different features to combine these functions. Also, when I ask, right, what is the Laplace of differential equation, these rules, of course, I'm going to use these rules, but we are going to need some other rules for the Laplace transformation. That is why we need to derive, okay, some other features from the definition so that I can use those rules for my differential equation linear Laplace transformation, guys. In the next session, I'm going to start teaching you the other features, and then we are going to use those features to take the Laplace of any given function.